Okay. Hello, everybody. I hope you can hear us. I'm going to start my presentation today. There's the in-situ Microscopy Alliance webinar. So, just to introduce myself, my name is Nicholas Randall from Alemnis, based in Switzerland. And in today's webinar, I'm going to give a brief introduction to the new in-situ Microscopy Alliance, which brings together a community of experts in electron microscopy and complementary analytical techniques. So the Alliance is driven by 4 analytical in-situ equipment producers and is supported by leading scientists. Alliance members can access webinars, workshops about new techniques and specific applications, as well as opportunities for academic and industrial collaborations and networking. So one of my colleagues in the Alliance, Greg Moldovan from Point Electronic, will be managing questions. So please type them into the Q&A section of the meeting during this webinar. We will be having a Q&A session at the end of the presentation with a representative from each of the 4 in-situ Microscopy Alliance companies present to answer them. So, what is the mission? Let me just check something. We have a little issue here. No, we're good. So, what is the mission of the In-Situ Microscopy Alliance? It's basically to advance in-situ microscopy technology and its contribution to a sustainable future. Secondly, to connect industry and academia to leverage in-situ microscopy characterization solutions, tools, and services. So, the In-Situ Microscopy Alliance was founded in February this year by 4 cutting-edge companies at the forefront of in-situ technology. So here we are at our first meeting at the Technical University of Munich, together with our first scientific advisor, Professor Marc-Georg Willinger from the Technical University of Munich. So the 4 companies are Alemnis, leader in situ micromechanical testing instruments; IMA Technologies, who offer high-precision robotic solutions for probing of electrical contacts; Nenovision, pioneer of the in-situ atomic force microscope, which combines the strengths of AFM and SEM; and Point Electronic, which develops detectors, electronics, and microscope control systems for SEM, FIB, TEM, and microanalyzers. So let me introduce Marc Willinger, who is one of our scientific advisors. Marc has been chair of electron microscopy at the Technical University of Munich for about 1 year. Before that, he was active at the ETH in Zurich and the Fritz Haber Institute of the Max Planck Society in Berlin. Since 2011, he is using in-situ SEM and TEM techniques for his research, which is focused on dynamic non-equilibrium states of materials and the emergence of function, for example, in catalysis and energy storage. So Marc will now say a few words and share his passion for in-situ characterization techniques.
Thank you, Nicholas. So, yeah, maybe first quick introduction. So the in-situ electron microscopy community has really largely focused on what can be done inside transmission electron microscopes. So these instruments are quite expensive, relatively rare, and yeah, you have to spend a lot of money first to get a high resolution TM instrument, and then you have to still need to buy in-situ equipment to observe materials in a functional state, which is what we want to do. But if you do in-situ electron microscopy in a transmission electron microscope, you usually have a lot of space limitations because the space between the pole pieces is really, really very narrow. And then what I find also, I mean, I don't want to speak against in-situ transmission electron microscopy. What I find also a bit limiting is that when you look into materials in a functional state, if you study, for example, catalysis, you often face situations where the dynamics are actually very fast in atomic level. So maybe if you click on the next slide, there's a little example. Yeah, you see here, for example, on the left side, a platinum particle on the serum oxide support as imaged in vacuum. And that's what has been done in electron microscopy for a long time. We have studied materials in the thermodynamic isolated state in vacuum where everything is sitting still. And we can nicely describe the positions of the atoms and everything. But as soon as we go into some functional state, in this case in the catalytic reaction, atomic motion starts to appear and pictures get blurry. So in the bottom row on the left side, you see the platinum particles. You lose this nice resolution of the individual atomic columns. And on the right side, you also see a particle in a catalytic reaction. There's a lot of reshuffling on the atomic level. And so the TM in situ community is focusing on atomistic dynamics, but there are lots of limitations. And I think, maybe if you click on the next slide, that it is very important to not only look into in situ TEM techniques, but also to consider in situ scanning electron microscopy. So compared to the transmission electron microscopes, scanning electron microscopes are very abundant. They're relatively cheap instruments. And the beautiful thing is that they have huge chambers. Yeah? So there's a lot of space that allows you to combine other tools into the same instrument. And that is what I find so fascinating about this in situ alliance. So we could, put different types of probes and detectors into a relatively large chamber and then combine different techniques. Yeah? And yeah, maybe if you go to the next slide, I have a few examples. First, maybe the combination I think I need to highlight. So if you have in situ electron microscopy on different scales, if you combine in situ scanning electron microscopy with this very local high resolution in situ transmission electron microscopy, then you can actually build up a multi-scale approach. You can look at local atomistic dynamics, and when they get too fast, or when you want to zoom out and look at collective processes that are linked with heat and mass transport, then you can continue in the scanning electron microscope. And as you see in this slide already, so I mentioned this before, you can combine different types of techniques like AFM or STM, transmission electron microscopy inside the STM. And yeah, maybe go to the next slide. Here are some examples. So we have in the past, in the last more than 10 years, tried out different things that can be done in a basically very elementary SEM, which just improved a bit the vacuum sealing, vacuum level, and we built gas feeding stations and analytics. And then we use this microscope for growth processes. On the top left side, you see nanowires growing, or we looked at the thin film dewetting processes. We looked at corrosion processes, but also into catalytic reactions, as you see on the bottom right side. So the SEM is really a very versatile tool. And together with this in situ alliance, we have the chance to come up with new ideas for different types of detectors. And that's a very nice way to further expand what can be done in electron microscopy. Yeah. And I think with this, I'm already giving back to the in situ alliance.
Thank you, Mark. Thank you very much. So really nice introduction. Thank you. Nice examples. And just for everyone who's listening, incidentally, Mark will be available for questions at the end of this webinar. So now let's look at the three main visionary themes of the In Situ Microscopy Alliance. So to create an ecosystem to enable both industrial and academic players to explore, develop and promote such techniques, tools and applications. So creation is big on the agenda. Education, so educating the research and engineering community about the capabilities of the various different types of characterization available today, and integrate advanced tools and applications for more comprehensive in situ characterization. So bringing them together to basically have additive techniques, so we can do several things at the same time. So the In Situ Microscopy Alliance is an ecosystem which consists of the 4 founding companies and a scientific advisory board. This board will be grown in the future to bring in experts in a range of in situ disciplines. Some of these board members will also be able to provide reference hubs in a specific domain. For example, we already have one at the Technical University of Munich, led by Marc-Georg Willinger, for catalysts and battery materials. In this way, we hope to grow the community and develop many new cutting-edge applications. So, to summarize, the Alliance is a community of experts in electron microscopy and complementary analytical techniques, moving towards a sustainable future. We're driven by, obviously, the in-situ equipment producers, and we're supported by leading scientists working on cutting-edge applications, so sustainable materials, energy storage, advanced semiconductors, just to give a few examples. So the Alliance members gain access to webinars and workshops about new techniques and specific applications, as well as opportunities for academic and industrial collaboration and networking. Now let's look at how the 4 companies of the Alliance come together. Here are some examples of the main products from each company. So signal acquisition and processing from Point Electronic, top left. AFM from Nenovision, bottom left. Nano indentation from Alemnis, top right. And nanoprobing from IMA. All of these systems are easily integrated into most scanning electron microscope chambers, where they can be used independently or in mutual collaboration. For example, a material of interest might be deformed mechanically while simultaneously measuring its piezoresistivity and viewing the material response in real time. So such a combination of techniques can therefore open up characterization possibilities which were not previously possible. Let's now view each founding company's products in a little more detail. Alemnis is based in Switzerland and is already established as a world leader in instruments for mechanical testing at the micro and nano scales. The video here shows just some of the many test methods which can be performed with such equipment. So nano indentation, beam bending, scratch testing, micropillar compression, high strain rate deformation, microtensile testing, structure compression, pillar splitting, fast mapping, fiber pushouts, bond shear testing and tribology, to name but a few. The Alemnis ASA has already been combined with the Nenovision AFM in a dedicated product, Lightscope, and can also be used easily with IMA robots and Point Electronic EBIC. Secondly, IMA Technologies, which is also based in Switzerland and has developed unique in-situ motion technologies, which allow electrical probes to be positioned with very high precision on a sample material of interest. Such MIBOTs are highly modular and compact, so several of them may be set up to work in unison or independently, depending on the application. So IMA robots can be combined with other characterization techniques, for example, nanoindentation, to look at electrical changes as a function of other stimuli. Nenovision is based in the Czech Republic and has developed an AFM, or atomic force microscope, which can be used in situ in an electron microscope. This means that an AFM image can be made of a surface while simultaneously observing it with the SEM. There are many advantages, such as the ability to correlate different data sets from the same sample region of interest. In addition, it's possible to locate very specific regions and image them with ultra-high resolution. This could be useful, for example, for studying the change in surface roughness when a material is subjected to an electrical potential or other external simulation. And finally, Point Electronic, who are based in Germany, are a provider of a range of hardware and software solutions for scanning electron microscopes, focused ion beam systems, transmission electron microscopes, and microanalyzers. On the hardware side, these include detectors, electronics, and microscope control systems. On the software side, these include dedicated software for data processing, giving complete solutions for topography measurement and electrical characterization methods, such as EBIC, electron beam induced current, EBAC, electron beam absorbed current, or STEBIC, scanning transmission electron beam induced current. In addition, Point Electronic provides unique modernization kits which can transform an older SEM or TEM with state-of-the-art control systems and software, thus extending their useful lifetime and allowing them to be used with other complementary in situ techniques. So to summarize the future action plan of the In-Situ Microscopy Alliance, we're joining forces to promote in-situ techniques. So you can expect to see us present in many conferences, exhibits, workshops, and meetings. We will be sharing the latest developments via webinars to show the community how different instrumental capabilities can be combined and for specific applications and specific material systems. This will then drive joint product development based on application demand and input from the community. Finally, all 4 companies are committed to dissemination of information in the form of dedicated education programs, the first of which will be an in-situ microscopy course planned at our Competence Center at the Technical University of Munich. So let me now thank you for following this first In-Situ Microscopy Alliance webinar. We ask you to please contact us if you have any questions, comments, or interesting new applications which you think could be enhanced using one or more of our complementary techniques. We're eager to interact with all of you and are passionate about furthering the scope of the in-situ field. So you can contact us via our website or through the LinkedIn group. See the links on this page. So let me now end this brief webinar with a question and answer session where a representative from each of the founding companies is available to comment. So if you want to ask a question and haven't done so already, you can type it into the Q&A section on the top of your screen. And Greg Moldovan from Point Electronic will be mediating the questions. So perhaps we can bring Greg into the call now. And Greg, perhaps you can tell us what questions we have. Can we perhaps bring in the rest of the panel as well, the experts from each of the 4 founding companies, if we have them?
Hi everyone. I hope I'm in the call.
Yes,
think everybody
see you,
else
Greg.
is here as well. Thank you. At first, thank you, Nick, for the introduction and for the summary and details. It's really wonderful, and I'm also very excited about this new alliance. And thanks, Mark, for the presentation, and thanks everyone for the questions that I have. We seem to have kind of 2 types of questions. One of them more around science and what is possible to do. Because I think, and these questions arise because all these companies were here together, and then also a little question about what the alliance will do. So maybe I start with this last one, and maybe ask this for Mark. I think this is more appropriate for you. Does the alliance plan to have a workshop or a tutorial? I don't know, a in-situ school in the future?
Yes, that is the plan, to have one summer school next year here in Munich, where we will have the different types of instruments equipped. So we have several SEMs running and with different features and instrumentation from the alliance partners, so that the participants can really do hands-on training. So there will be lecturing and also practical workshop.
Good. And then another question, since I have you, is, I think we all have shown over time the advantages of each of our products, and one theme that comes through is what is the advantage of combining them? What is it that it brings us together? So, for example, what are the advantages of combining the AFM, SEM, and micromechanical testing? What brings all of us together from a science point of view?
So yeah, when you do an experiment, you try to get as much as information about the state of your material that you can get. So you try to look with different probes, and of course now when we have the electron beam, we can generate a picture, we can do elemental measurements and so on. But then if we have additional tools, like to look at the topography or like the magnetic structure, then we don't need to run for each experiment to a different instrument. We can combine all at the same time, at the same place, under the same conditions. And that's a huge advantage. And the instrument platform, the SEM, is just, as I mentioned before, optimal for that, because there's enough space. So you can combine multiple tools and then combine the advantages of all these complementary probes that we can now combine.
Wonderful, good. And following on the same topic, what is the advantage of combining mechanical tests with electrical tests? Maybe this is a question also for Emina. And you know, what is the typical applications for this? And is it possible to do this since the nanoprobing is also in the way? Will that somehow interfere with the other signals?
Do we have someone from IMA on the call? I don't see anybody.
Hi, Greg. There is Tom from Nenovision. We got the issue with connecting the IMINA. If you can answer their question.
Okay. Well, maybe I can answer it in the meantime. Yeah. So, well, I think the question was combining things like nanoprobing with mechanical testing.
Mechanical tests, yes.
I can see many interesting applications. So, for example, if you take a piezoresistive film, if you deform that film, you're going to change the piezoresistivity. What's interesting today in many applications is to understand that deformation from an electrical perspective. So say you're talking about a touch screen or a bank cash machine. Those screens are piezoresistive coatings, and we want to know what resistance we have at a certain distance from the deformation. So we can make a controlled indentation and maybe have an IMA robot at a certain distance from that contact and measure within the thin film what is the piezoresistivity at different positions. So that's one. Another obvious one is if you damage bonding, when you shear a bonding from a semiconductor, you can use the electrical probe to see how that's affecting the conductivity in the system. So I think there's a lot of potential for combining electrical measurement with mechanical deformation, for sure.
Since Emina not managed to connect, I can perhaps answer a little bit around the compatibility with between detectors and having the electrical probing system in. It's quite normal to use electrical nanoprobing together with SE detector. It's quite normal to use it with backscatter detectors. There shouldn't be any difficulty in managing. Of course, if you want to combine it with a STEM detector, then I think you will have to stop and think how you're going to do that. But there are no fundamental reasons. They're all just practical reasons. But there are a few more questions, and I would like to move on. Maybe this is for Nenovision. Maybe Radek, you can take this one. I think what's happening is that we all bring in different users and different scientists, maybe from different fields, and they're still discovering things. Is it possible to do AFM and SCM measurements in real time? And in what the usefulness of that? What properties can be measured?
Yes, it is possible to acquire both images from SCM and AFM at the same time. We are using the techniques called sample scanning, where we fix the electron beam and the probe in the fixed position, and we are moving with the sample below them. Thanks to that, it's easy to correlate acquired images, and you can get information like topography, mechanical properties, electrical, or electromechanical properties.
Thank you. And then a practical question, and maybe Mark, you can take this. This is more on an SCM or TEM question. Is it possible to determine particle size SEM? And I suspect the answer is yes. I think the question is, how far you can take it. Whether would TEM be a better option for measuring particle size?
I guess this depends a bit on the particle size regime you expect. So if you have something that is like below 2 nanometers, then I would rather go to the TEM. But if you want to have like a large overview, it depends on the substrate on which the particles are. You can use both techniques, definitely. Yeah.
Okay. I think with this, I kind of gone over the questions that I picked up. I suspect if anybody has any burning questions, now is the moment. If not, you can always get in touch with us. The web address is on screen, and you can also, of course, write to any other company individually. We always speak amongst ourselves, so we can circulate questions if needed.
And I think one of the key things here, Greg, is that we're also interested really in developing new applications. So if people who are listening have ideas, even if they may sound a bit crazy, we're really eager to listen to them, because we want to try and step out of the conventional box, and we want to try and combine these techniques. As Mark was saying, the interest is in doing it simultaneously. Before, we could do one measurement and then we take the sample, go to another SEM or change out the equipment. Well, we've just oxidized the sample, or we've just lost the advantage of latency. So if we can do it all simultaneously in the same chamber, we really can do some interesting science that couldn't be done previously. And that's our passion, really. It's to try and find these applications and then develop the equipment and the simultaneous operation that would allow us to implement it.
And that's also the point where I see the huge potential. So you have all these fine and precise tools, probes, and we have the microscope. But by controlling the environment, like the atmosphere composition, so which types of gases we introduce into the chamber, and the temperature, for example, we can study, battery materials, or, as I've said before, chemical reactions, and then combine AFM with in situ experiments in gases or mechanical properties under the influence of different gas species and temperature. So this combination of a controlled environment with all these probes, I think that is the thing that opens the gate to new possibilities.
Yeah. Well, great. Thank you very much, everybody.
Thank you.
That was very interesting. Would anybody like to add something before we wrap up this webinar? No? Well, in that case, thank you very much to the organizers, Nenovision in this case, and thank you very much to Mark for being available and Greg for doing the questions. And we hope to meet some of you soon around an SEM chamber doing some cutting edge science. So thank you.
Thank you.
Goodbye.
Thank you very much.
Bye.
Bye.
Okay. Bye. Bye.